All right, our last objective for this unit is to find the volumes of base solids. Notice this does not say the word rotate or revolve. Base solids are made when there's a flat surface on the bottom of something, and coming up from that flat surface, you have shapes of a different kind. So in this case, it says that the shapes are semicircles, and we'll get to this in a second, but what that means is if you have some shape, coming up from that shape, everything would be a semicircle. So semicircle, 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 semicircle. If I were to connect all these, it would kind of look like, I don't know, like a loaf of French bread maybe, where the bottom is flat and then every cross section is the same shape. We could do this with everything, and we certainly will in class. But the basic idea of this is this. The formula for base solids, this is by far the easiest one, is there will be some coefficient and then it'll be the integral of some function squared. And that coefficient changes based on whatever the shape is. So semicircles that we just did, the coefficient will always be pi over 8. And I can easily show you the math where that comes from, but it's always pi over 8. Squares, the coefficient's always 1. Equilateral triangles, the coefficient is always root 3 over 4. Isosceles right triangles, the coefficient is always 1/2. Rectangles, it depends on what the ratio is. If the height is 10 times the base, then it's 10. If the height is 12 times the base, it's 12. So I always just put n here for just whatever that ratio is. But you can just kind of memorize these. It'll always be these. So when we look back at this, it asks for the volume of a solid created when this function and the area between that and the x-axis between 1 and 3 creates semicircles. So semicircles, the coefficient is pi over 8. And then we have integral from 1 to 3. And it just said the area between this and the x-axis, so that's just one function. So I'm going to write 4x plus 1 squared. I'm realizing, I don't know if I said this, but back here, that squared is important. That'll always be there. And put a dx at the end, and that's it. So we could evaluate this if we wanted to. We'd probably do u substitution, where u is 4x plus 1, but the rest of this is old stuff. Our second example, we're going to do the same thing. The difference here is that they gave us functions, 2 of them, so x squared and x to the 4th. They didn't give us limits, but they did tell us that the base solid, the cross sections are squares. So I can set this up right now. I know it's going to be the integral with a 1 out front because of the squares. So off to the side, I need to find the limits. So I need to set x squared equal x to the 4th. I just know the answer to this. You probably do too. The values that make this true are going to be 0 and 1. So our integral goes from 0 to 1. And you can test this out if you want to see what's higher, but I know that in between 0 and 1, x squared is higher. So it's going to be x squared minus x to the 4th. So that's the height here. And then that will be squared. This is always the case for these base solids, that these are always subtracted inside of the squared, never outside. There will never be a time for base solids where that occurs. So I'll put a dx here, and we're done with this. You can easily solve this if you want to. You'd have to FOIL it out first to take the integral, but the setup is what's new about this. So our objective today was we were finding the volume of base solids with known cross sections using these volume formula.